Thank you for your patience and for coming to this lunch session, especially since the one where mysteriously disappeared from yesterday. I'm going to show you today how science has been democratized. What do I mean by democratized? For centuries, maybe even 1,000 years, astronomers would go and collect data and store it in a shoebox. And they would take notes on locations of the planets, and even when they called them astrologers back then. But it was something that data was their power, it was their ability to understand. And they sequestered those in shoeboxes, and eventually the shoeboxes became hard drives. But still, until they were ready to write a paper, a lot of the information gathered from telescopes and gathered from institutions basically was property of the institutions, and visiting scientists were allowed to look at it. But oftentimes, this information, because of a practical nature of its transmission, as well as because of the nature of wanting to be able to study that data, it was kept in these shoeboxes. And the digital age came, and it still was kept in shoeboxes or hard drives. And a while ago, a gentleman named Jim Gray, who's a Microsoft researcher, and Alex Islay from Johns Hopkins University got together and started looking at the trend in telescopes becoming larger and larger and more expensive and fewer of them, which limited access to astronomers actually having physical access. But at the same time, CCD chips and data processing was making the images collected by these telescopes deeper and deeper and larger until essentially the institutions that were collecting this data had no possibility of ever processing all of it. And so these shoeboxes now became full, and many people never even saw what was in them. And so they came up with a concept of being able to put up this information from these surveys, and it started with the Sloan Digital Sky Survey and Sky Server, but to put it online on the internet as a worldwide telescope to be able to have astronomers come in from around the world and get access at that data, run queries on it. And this data also, because some of it was getting so big, the actual transmission of being able to send disk packs or tapes or something was a practical limitation. So being able to have things rendered and stored in a way that could be accessed over the internet with relatively slow connections compared to the data size, but be able to have that available to everybody. So where I come into this, and I'm Jonathan Fay from Microsoft Research. I'm a principal research software design engineer. I consider myself a professional developer and an amateur astronomer. But I got together with Curtis Wong and Jim Gray to look at taking that for a step further from other astronomers accessing this data over the web to bringing it out to visualized by the public. And Curtis had some very powerful thoughts about how to take a tool experience and narrative and contextual inquiry and be able to put them all together in an application that was a tool plus narratives, plus information and data access, all together weaved so that scientists, kids, educators, students, everybody could actually use this tool and get a lot out of it. And this concept evolved into what was launched last May as Initial Worldwide Telescope. And this morning, we just turned live Worldwide Telescope Equinox, which brings a whole new level of data to it. So first of all, context is one of the most important things we want to have with Worldwide Telescope. So I'm going to start out by showing where our context is. So in this case here, this is our home plate. Actually, it's not home plate, it's the pitcher's mound at Dodger Stadium. But the context that we're in here is in Dodger Stadium. And the context is the Los Angeles area. And the context is California. And the context is the Earth. And from the Earth, our context is that we're in a solar system. And we're in the Milky Way amongst millions and billions of stars. And in that, we actually come out and you can see the Milky Way itself disappearing. And eventually, we're one of billions and billions of galaxies. And this right here, we just zoomed out from the home plate to viewing the entire visible universe up until just a short time, relatively speaking, after the Big Bang. And we can look and see the large-scale structure of the universe. And so you've now seen the context of being able to have all of this data that expresses the context from the Earth to the sky, and be able to have that in a seamless environment where now you're going through orders of magnitude. Well, how did we do this? First of all, we used off-the-shelf Microsoft tools, SQL Server, IIS, C#, DirectX, and a small team of developers. In fact, the client that you're looking at right now, almost every line of code I wrote in my office. So an application like this is not something that is completely inaccessible and only going to happen with a large team. Now, of course, this is pulling together data from the web, from other institutions, that billions of dollars have been spent in order to get that out there. And by using the software plus services approach, we're able to bring it and make it visible. So I'm going to show you some of the other ways that Worldwide Telescope can be used. So first of all, what you were seeing was the new 3D solar system and universe mode that's part of Equinox. And that allows you to go through the solar system and see the concept. And we'll get back to that a little later. But you can also, the primary mode that we launched last year was being able to see the sky as seen from Earth from the collection of all the great observatories. So for instance, right now, we are looking at Cygnus, and right in our crosshairs is the North American Nebula. I've never understood why they call it that, but evidently there was some reasoning behind it. But as we're looking at this, you see that the interface is very visual. We have at the bottom here our context search, which gives you access to the interesting objects that are in the area of your field of view. And automatically, as you move your view around and see other things, we'll move over here and head on over and drop back in. And we'll find some other interesting objects. Now, as you see, we have some images here: Classic Beauty, Whirlpool Galaxy, M51, Out of This World, and then the catalog entries for it. This set of colliding galaxies is known as M51. And as we're zooming in on this, you notice that the image itself progressively refined. It was a little blurry at first, and then it came into focus. So how did we do this in software? First of all, we took the sky and we chopped it up. For this particular survey is a 1 terapixel image. So that's 1 million pixels by 1 million pixels. Now, if you did a BMP equals new bitmap and that file, how long do you think it would take? And does anyone have a machine that would actually, not immediately throw an exception on that? So obviously, storing the data like that is not very practical. The way astronomers originally stored this data was 1,800 individual pointings in the sky, and then several plates for each of those pointings in different bands. And each of those files was 23,500 by 23,500, and there was a lot of overlap, and the coordinate systems, there was data for those coordinate systems, but essentially you had this file and you could hardly load it or even download it from a time-wise, and there was no software on a PC to even visualize this. So what we did was create a mosaic of the sky that put all of this in its proper perspective, and we have a single image that's 256 pixels by 256 pixels that actually maps the entire sky. And that's the starting point. We divide that into 4, and each of those 4 become 256 by 256. And we recursively do this until we get to our 1 million by 1 million or 1 megapixel by 1 megapixel image. Now what that allows us to do is it's called a tiled multi-resolution map. And this is something that was pioneered for geography by Jim Gray and Tom Barkley in the TerraServer product. And of course, a lot of other products, you know, Virtual Earth, Google Earth, the Zoom technologies that are in Silverlight with Deep Zoom. A lot of this technology has really taken off. But at the type of scale that we're doing this, it's essentially the same thing you can do with Deep Zoom, but applied to just a very large data set. So now that we're here, we have to realize that for several thousand years, the sky has been people have been looking at the sky and taking individual drawings and then eventually photographs and CCD, but they would take a picture of a small area. While the Earth when it was mapped, they would use these projections that would show it flat so that you could put it on a placemat at a seafood restaurant. But if you try to wrap that around a sphere into the sky, as you know, Alaska really isn't as big as Africa, although it looks that way on one of these maps. That's not the reality. And when you start distorting the sky that way, it becomes very problematic. In fact, the projections that you usually see the Earth in, you can't even see the poles at all. The poles are just missing altogether. Antarctica, a slice of it is, you know, turned into this mammoth. Oftentimes that you're not even able to project that. So the current technologies that were applied to computers and GIS just didn't even deal with the poles. So we had to figure out also how to take, mathematically, how to take the entire sky and map it onto a sphere. Now, there have been things like equirectangular, like people have seen panoramas that are equirectangular that have a similar technique. But the problem is that at the poles you have a singularity, and at the levels of detail that we have, you would essentially have to have a near infinite amount of memory to look at the 1 pixel around the pole, while the equator takes, you know, 1 pixel. And so that really inhibited being able to view the sky without some major distortion. So we created this system which essentially starts with an octahedron and allows you to map the North Pole to the top of the octahedron, and then the equator to the square that's inside the square of your texture. And so in the end, your poles are in the center and on the corners, and it's almost equal area, and there are no singularities. And so essentially, we now can have spherical maps, panoramas, planets, without having to the pitfalls that have been involved for GIS and Earth-type products. So the other thing is that humans see things visually in visible light, which our eyes are sensitive to it, but the types of cameras that have been created, in fact, how many people saw Jodie Foster in Contact? You may have seen these, the very large array here. So what does that look like when you see a picture taken by the Very Large Array? Also, by the way, just to let you know, I installed Worldwide Telescope about 3 seconds before we started all this monitor mishap up here. And so what you're seeing is exactly the experience you'd get the first time you ran this and access these data sets. So we're coming in here and zooming in the radio spectrum. And so this is an image that's been created from those dishes by doing some mathematical interpretation of signals. And basically, here you see this very bright radio spot here, and that's from a pulsar. And I'll come back to that in a few seconds. So that's radio, and that's the lowest end of the spectrum, very long waves, low energy. Then there's the cosmic background radiation. And this right here is what's called WMAP, and this is a satellite that went off and measured the afterglow of the Big Bang. And about 3 degrees above absolute zero is this microwave signal that permeates all of space. and they processed this so that you could actually see how the structure of the universe and what is theorized right now is that basically quantum fluctuations early on in the Big Bang created the whole structure of the large scale of the universe. And so these tiny variations essentially led to the type of structure. And so that's, scientists use this to kind of study that. But it's also very interesting to be able to see the correlation. Other things like looking at the dust in our galaxy. So right now we're loading in and looking at the glow from the dust in our galaxy. And so when you look at the Milky Way and you see kind of dark parts, if you're in a really nice dark sky environment, you see dark parts amongst the stars, that is the dust that you're looking at. And it actually blocks light in the visible spectrum, but in the infrared spectrum and lower frequencies, it actually emits a glow. And so we photographed that, and this really is useful for helping map out where interesting things are happening, because essentially the condensation of this dust is which leads to nebulas and star formation. We also have infrared here, and so we can look at the same Milky Way galaxy in infrared. We have other bands, the Sloan Digital Sky Survey and Galix in ultraviolet. And one of my favorites here is ROSAT, which is an X-ray full sky. And so this is basically the X-ray signature of that pulsar that I showed you earlier. Do you remember when we were looking at that pulsar in the radio spectrum? And so let's go ahead and set the background imagery to our visual and our foreground imagery to the X-ray. And we're going to go take a trip into this X-ray source. And so X-ray is very high energy, so whatever is doing this must have been some catastrophic event. And in fact, it was a supernova. And about 1,000 years ago, it's a star that exploded and left this remnant here. And so as we're coming in here, we're seeing the detail load. And this supernova itself, about 1,000 years ago, it was seen by the Chinese, and even the American Indians painted on the caves a picture of this star in the daylight. And this was so bright you could see it in the daylight. But now you can actually cross-reference the X-ray signature and the supernova itself. And then you can go in and see the detail in visual from the digitized sky survey, and then switch over and see that detail from Hubble Space Telescope. And so now we're looking at images from Hubble, and these are all registered together in the sky and all downloaded on the fly from the internet. And we can then compare that to look at the gas jets coming out of the center of this supernova remnant. And so this star has a tremendous amount of excitement and because of the whole physics of everything that's going on, this is what it actually looks like in X-ray at very high level of detail. So we've now brought together within seconds images that before, imagine a few years ago you would have had to have driven over from one observatory to another, gotten plates, brought the plates together, and worked on them. And you would have had to make copies of the plates because they'd never let the originals out. So part of this ability to bring all of this data together and make it accessible has given people to start looking into their shoeboxes to see what else that they could bring out. So for instance, the Harvard Observatory has collected over the last 100 years 500,000 glass plates. And these are very big plates that are actually fairly high resolution photographically. And while they're not as deep as CCD, it represents 100 years of history. And if you can imagine that supernova that we just looked at that happened 1,000 years ago, this is 10% of that supernova's life from that. And so being able to actually take 100 years worth of data, look at a spot in the sky, and see it over 100 years as it transforms. And some things are going to be seemingly changeless, even for thousands or millions of years, or even billions of years. Our star wouldn't look all that much different from 1 billion years ago. But some things are going to change. And where you're seeing change, that's something that's very interesting to astronomers. So in this massive amounts of data that we have, how in the world can you possibly understand everything that's going on with all this data? It can get to be overwhelming. It's like amazing that you have this power, but where do you even start? And so part of that, we get into the narrative, which is our guided tours system. And so when I click on the guided tours, it's going to go to the server and bring down a list of the published tours that are available to us. So we have different categories here, and I'm going to pick one from Nebula here. And this is a tour I'm going to play for you here, and I'm going to let it go quite a ways so you kind of understand a little bit about what type of data we have. This is from the Harvard-Smithsonian Center for Astrophysics, Alyssa Goodman, who's a well-known astronomer, and she's narrating this tour regarding dust and how it comes to play. If you guys remember, I showed you some of the Milky Way and the big bright red dust map. Well, she's going to go into a little bit more explanation about that, assuming that the internet connection will do this. So one of the set of tours that we have available right now are going yes, there's going to be audio on this. Hold on one second. Good thing we had a. Okay, I'll pause this and restart it. So the tours themselves, right now we have a collection of tours from educators, from different contributors in science and cosmology, and we also have this community system in which essentially anybody who has an interest in aggregating data regarding some part of astronomy or earth sciences can create a community and basically have people post to that, have people share the information with one another, share tours, and have that available with each other. We have a careful curation process that we go through for the guided tours that we publish directly on Worldwide Telescope, but we let each individual community police their own material for their own community. I guess you can imagine that if we had, one of these wackos who believes that we're all going to be dead in 2012 because of the Mayan calendar and showing Planet X careening down on us or something, that some of the scientists who contribute data may not want to have some of those baseless theories thrown out there. And so that's why we keep a little bit more careful curation, but we want people to explore with each other. And you know what? If those wackos get together and create their own community and start sharing the data, eventually people will look at it and say, wait a second, there is no data to back this up, and not believe it. Or they'll be able to say, hey, this theory actually has some weight. But at least it'll have the ability to have their own sandbox where they can do that. So do we have audio now? We need more boost on the volume. I'm hearing just the tiniest bit right now. I don't know if it's coming from the speaker. Okay, so I'll let him work on that, and I'll move on to show you some of the 3D solar system mode first. That sounded like something interesting. I turned off the audio, so...
The Milky Way is a spiral galaxy, but it's hard to see that because we're inside it. Here's a spiral galaxy not far from us, about 12 million light years away, called M81. If we look at it in optical light, we see billions of stars shining together in a spiral pattern. If we look at the heat from M81 rather than the light, it looks like the false color orangey image we see here. This Spitzer Space Telescope image uses long wavelength cameras that can see heat, just like the one that took the picture of this cat. Galaxies are filled with tiny particles called dust that absorb the light from stars and re-radiate it as heat. The dust is actually a kind of smoky haze that fills much of the space between the stars, and even though it's very cold, we can still see its glow. In our own galaxy, astronomers use dust to map out the matter that is most likely to form new stars. Let's zoom out 12 million light years back to our own galaxy, the Milky Way, and take a look at dust there, which is the black smudgy looking stuff in this image. What you see here is actually the very center of the Milky Way galaxy, but it's hard to tell that because we're inside it. If we could see it from outside, it would look like a thin spiral disk, but we're stuck inside, so the disk of the galaxy just looks like the bright band of stars we see as the Milky Way on dark nights. The dust glows at long wavelengths, just the way we saw it in image.
So now we basically started feeling like we were watching the Discovery Channel. But the amazing part about this is that you can stop and you can go forward and backward and hunt around and look, use the context information to find out more about it. You can link to related tours. And essentially, you had a tour guide there, but you can at any time decide to break off, go and explore a little bit, and then
the dust
unpause
glows
it
at long wavelengths,
and go right back to
just
where
the way
you
we
were.
saw it.
So this environment, as you can imagine, now the context of what all that data meant that I showed you earlier starts having meaning when you have someone who knows about this, who can narrate it. So that was a professional astronomer who was narrating. And we're going to go to a slightly different level. And this is one of the few tours that we put up on our Worldwide Telescope site that we decided it just had to be shown to everybody rather than being put into a community. So in just 1 second, we'll start out, and it will be self-explanatory.
Hi, my name is Benjamin. I am 6 years old and I live here. Actually, I live over here in a big city called Toronto. On clear nights when I look up in the sky, I see something like this. The tour I want to take you on is of the Ring Nebula, which Wikipedia, the Free Encyclopedia, also calls M57. I don't know what that means really, but I think it's like a jewel in the sky. The Ring Nebula is in the constellation of Lyra. Lyra is also where the brightest star in the sky is. This star is called Vega. The Ring Nebula is a little ways away from Vega over here. My dad says that he doesn't think the Ring Nebula is too far away. I read that it's 2,300 light years away, which seems like a very long bike ride. This is not how I see the Ring Nebula. I see it like this. The Ring Nebula was discovered a long time ago by someone in France. This picture of the nebula is beautiful. It looks like a precious blue gem in the middle of some red orangey stuff that looks like fire. I read that's because different gases give off different colors. You can see green, yellow, red, and blue. A nebula is what happens when a star like our sun dies. It lets out its remaining energy and expands, making lots of pretty pieces that one day can become planets. I think it's neat that stars can be so amazing for so long. I wonder what Vega will look like when it dies. That's my tour. I hope you liked it as much as I liked making it.
So you can imagine the emotional response that you get out of watching that thing. It's just, when I told you that I was the sole developer on the client, I've had certainly support in some of the web development and the data curation, and but it's meant burying myself sometimes 100 hours a week, not coming home. I've got 5 kids of my own. And, not coming home sometimes because I was up all night working on this. And sometimes that sacrifice is kind of hard to fathom when you're a developer working on something like this that you're really passionate about. It's sometimes hard for the spouses who consider themselves computer widows to deal with that. When my wife saw this tour, she said, "That's why you spend all those hours." And so, it's one of those, sorry if I'm a little emotional over that, but, it's a possibility that within a reasonable amount of time that you all getting an inspirational idea with good tools and good technique can think about doing something that's going to change the world, whether it's for making a gorgeous implementation of an interface for a business that's really going to get a lot of value out of it, or whether it's something that's going to go out to the web and show off some product or service or something. It's bring passion to the development that you make. Do something that's really going to immerse people and get them excited about it. Some of the other aspects as we get into the technical development of this is how do we make then the software services architecture get at this terabytes and terabytes of data in a way that's efficient. So first of all, there's a couple of decisions we made in the user interface. One of which is when I'm moving, even when we were playing the tour, there were a couple of spots where the internet got really slow. And given the amount of stress that we have in the system here and all the hall and everybody using it, that's going to happen on it. But when that is going on, and like right here, we're having, it's a little bit slower, but I'm not holding up the UI. I can still move around. I'm not stuck waiting for the internet while I'm interacting. That's a really important part in developing your applications. With managed code now, threads are easy to access. Use background threads, do the processing. The other thing is finding out and prioritizing what's the most important thing to download. A lot of people and researchers have going in and seen some of how we handled our downloading over very slow connections. And we're like, oh, are you making predictive models, or are you looking where the user's going? And part of it, so we went down to no, it's a whole lot simpler than that. Is what are you looking at, and what is the most important image to have right now, and make that decision every millisecond, every time you're reevaluating how you're going to commit yourself to one more tile over the network, to decide what's the most important one. So first, what covers the largest area of the screen? Secondly, what's the most central portion? And so the way we work is we have the user interface thread completely free of having to deal with internet downloads. And it essentially renders what's available. And it uses the best image available and then stretches it if it needs to in order to cover the area. We try not to show anybody blackness unless in fact is black sky, which happens in space. But you essentially don't want to show all white, all black. You want to use whatever information you have to give the best impression that you can. Secondly is in the background, we have a queue and a cache that's constantly deciding how to use the precious resources of the graphics hardware and your internet connection to decide which tiles are most likely, what parts of the image are most likely to be needed in the future, what do we need now in order to display a better image, and what should we throw away because we need space. Given that this has to run on machines that run in schools and stuff, that sometimes if you're lucky to have any 3D graphics at all, much less a gigabyte of RAM, so a VRAM. So we had to really make a lot of decisions about tuning that and figuring out how to do that. And again, with the threading model in .NET, it's just really great to be able to have all this working and not have to worry about crashing your application because you missed something. At this point, we're going to be running out of time soon, and I'd like to open things up for questions. But I'm going to start going around our solar system and visiting a few things while you guys get ready for the questions. This is Jupiter, and we're going to look at Jupiter and see what Galileo saw about 400 years ago when he first pointed his telescope at the night sky. He saw things moving around Jupiter. And I'm going to go to full screen mode here for a second so you can really see this. Yeah, we're getting the time. So as we're looking at this here, you're actually able to move the time clock to go fast forward and see the orbiting of Jupiter's moons. We can pull back away from that. And let's go ahead and take a look over here at Saturn. And we can see Saturn in rotation. We can see the rings. You can see the details in the Cassini divisions. You can go into Mars. And we actually have digital elevation models with Mars here that allow us to take a look at the detail inside of Mars, on the surface of Mars. And we'll actually have resolution on Mars soon that will rival the best photography of Earth. So anyway, are we ready for some questions?
So how much, where is all this imagery being stored?
So
how big is it?
And how big is it? Well, first of all, if I know that number at any given time, marketing always comes up and says, oh, what's the number? Give us some big number, because everybody likes to have big numbers in press releases. And really, I'd have to make something up in order to put a number on it, because the idea is this data is distributed across the web. Some of it that's very highly in demand, we cache in our servers, some in Redmond and some in Virginia in our data center, the Virtual Earth Data Center. And that data we do know and can control, and I think it's somewhere between 12 and 20 terabytes or something like that that's in the cache files right there. But there is hundreds of terabytes of data on the net that we can dynamically go to, and people can plug in their own data, other astronomers. A lot of the astronomy organizations that are space telescopes and other observatories are putting their data online and then having links to what's called a WTML file that basically is a description of the astronomy data that's available and allows Worldwide Telescope to view that.
So do people do you give them tools for creating the data in the form that you expect it?
Yes, we do have tools that are published, and there's a developer and data curation website that will be available shortly with the tools and you can download them. And you can also, if you're an amateur astronomer, you can do a file open, and if you have AVM tags in your images, it will load right into the sky. If they don't, you can use the Control-E hotkey to open it in edit mode and align it yourself. Okay, another question?
Looks absolutely fantastic. Nice work. Just a question on, is it possible, or have you guys thought about what other things you might visualize with this technology? For example, complex systems or data, vast amounts of data. It'd be interesting to be able to, in 3D, visualize certain things aside from the universe. The universe is, the best, but other applications.
And the answer is yes, and they would hang me up by a noose if I talked about this, because we're not ready to talk about anything press-wise right now. But yeah, we are thinking about that, and that definitely is something that enters our consciousness right now.
You said
Yes.
that.
Okay, so the one last one, and then I have to cut it off.
You said that you had 100 years of Harvard glass plates, and sometimes something significant happens over that amount of time. Do you have a way of visualizing that history?
Okay, so right now, what I mentioned was that it's inspired them to open their shoebox. They're taking a scanner right now and working on scanning all that plates. It's about a 3-year project. And so we will have that up at that point. That data isn't live, and I should have made that a little more clear. But that's something where people are, because of this openness, they're going back and looking at that data. So it will be available. It's not up right now.
All right, how would you visualize that? Just like the rotating of Mars?
So part of this is, like we were seeing rotations of the planets and stars, we also have like eclipses and things, because we have the time element here, and you can set your observing time and your observing location. So they're about to pull the cane on me, so thank you all for coming. And this is all available at www.worldwidetelescope.org. It's a free application. I encourage you, please share it with school teachers, with your friends, with your kids. This is a free, no advertising involved. It's a completely done as a service to the education community. Thank you very much for coming.